what a log function looks like by looking at its equation. So if you change this value or this value on this function, you should know how that affects what the graph looks like. So let's first look at what the base change does to the graph. Okay, so here's a log of base 20. If we go to a log base 10, or if we go to a lower base to a base of 1.1, the log function straightens out. Okay, so base 10 gets a bit more bent, and then as you increase the base higher, it gets a little bit more bent, so to speak. But notice the x-intercept doesn't change. It's still going through the x-axis at 1. It's still an increasing function, so it's starting in quadrant 4, ending in quadrant 1. Let's have a look next at what we do, what happens to the graph when we change A. Okay, so again, looking at the graph, let's go back to a base 10. Okay, so the number out front, what happens if it increases towards the positive end? Okay, higher and higher. Okay, it seems to increase a bit quicker as the number out front gets larger towards the positive. So it increases, and no matter what value you pick out front, it seems to have the same x-intercept, so it still crosses at 1. What happens if we decrease to a negative in front of the log? Well, now the function is decreasing. It goes from quadrant 1 to quadrant 4, and if we increase it further, it decreases a little quicker. Okay, so the bottom line, in general, the domain of a log function, x is greater than 0. Okay, it stays to the right of the y-axis. It's to the right here. So that's y, that's x. It lives in this region. Alright, the range is an element of real numbers. Okay, so the graph continues off towards infinity, towards the positive y, the negative y values. Okay, the x-intercept is 1. Regardless of what we choose for the base or the number out front there, A, x-intercept is 1, and there is no y-intercept. You need to be able to convert from log form to exponential form and back. You won't need to remember these two equations. They will be supplied on your formula sheet. A good strategy to use when converting between these forms is to start with the base, jump across the equal sign to get the base neighbor in the other form that you're converting to. Let's see what I mean by an example. Y equals log of x. The base on this is 10. If you see a log with no base written explicitly, you can assume that it's a 10. Start with the base, go across the equal sign to get its neighbor in the other form. So in exponential form, we have 10 raised to the power of y. Then we come back and pick up the last term. Another example, y equals 2 times natural log of x. Now the base on this logarithm is the base e. So there would be an e right here, but it's not written explicitly. So we can write log base e of x or ln of x. ln of x is shorter, so that's the way that you'll see it written most often. If we want to convert this equation to exponential form, we have a bit of a problem. The form that we have to compare with doesn't have anything out front. This one does. So we need to get rid of the 2 first. Divide both sides by 2, and now we have a form looking more like it does above. So again, you start with the base. The base here is 2. Go across the equation sign to pick up its neighbor in exponential form. So e to the y over 2, and then come back and pick up the last term. Another example, x equals log base 1/2 of 100. X equals log base 1/2 of 100. Don't panic if you see a fraction, it's still just a base. We treat it the same. Start with the base, go across the equation sign to pick up the neighbor in the other form. So 1/2 raised to the x, and then come back and pick up the last term. Okay, if we go from exponential to logarithmic form with this example, we start with the base, go across the equation sign to pick up its neighbor in log form. So we would write log base 4 of 1/64, and then come back and pick up the last term. Another example, just erase there. E to the x equals 0.25. Again, we start with the base, go across the equation sign to pick up its neighbor in log form. So log base e of 0.25, and then come back for the exponent. Okay, so we can just write this as ln of 0.25 equals x. Last example, 2 to the w equals x. Again, we start with the base, so the base is 2. Go across the equation sign to pick up the neighbor, so log base 2 of x, and come back for the last term. You should know how to evaluate logarithmic expressions. Evaluate just means what is a log expression equal to. One of the strategies that we touched on in class was to arrange so that the base of the log and the base of the argument were the same. Once you get this set up, the answer is just the exponent. So in this case, it's just x. Another strategy we looked at, if you see a log base 10 or a natural log, so a log base e, you just use your calculator. We have buttons for those. Another strategy we have is the log of any base evaluated at 1 is 0. So this comes from the function properties. If you look at the graph in this area, so the log evaluated at this point at 1 is 0. So the y value here is 0. And lastly, the log of any base evaluated at 0 or evaluated at a negative number is impossible. Reason for that being, the log function lives to the right of this y-axis. It doesn't touch the y-axis, and it doesn't venture into this area. It lives on this side. So if you try to take the log function and evaluate it at x equals 0 or a negative number, it's impossible. Let's look at a few examples evaluating log expressions. If we try to evaluate log base 2 at 0, this is impossible. Remember, the log of any base evaluated at 0 is impossible. Same with this. So if it's a log base e evaluated at 0, it's also impossible. Okay, in this we will try to get the argument base to be the same as the log base, so we can express 27 as 3 cubed. So now we have the log base the same as the argument base, so the answer is just the exponent, this one. Okay, let's look at another example. Log base 2 of 64. So again, we try to get the argument base to be the same as the log base. So log base 2. 2 raised to what power gives 64? So you could guess and test at this point. 2 raised to the 6th power turns out to be 64. Subtract log base 2, and you can express 4 as 2 squared. Okay, so now we have the bases the same for this one. So we would write just the exponent is the answer. Okay, and we also have the bases the same here. So the answer here is just the exponent. So 6 minus 2 is just 4. Another example. Log base 7 of 1/7 minus log base 1/5 of 125. So we want to get the log base and the argument base to be the same. So in order to do that for the first term, well, you can express 1/7 as 7 to the minus 1. Those are the same, so 7 to the minus 1 is written there. Okay, looking at the second one, 1/5 and 125. I want to get those to be the same base. So eventually I want to get 125 to be 1/5 raised to some power. Okay, we know that 125 is just 5 cubed. So if we do 1 over 5 to the minus 3, this is also the same as 125. So that's what we'll do below. So we write log 1/5, and 125 is the same as 1/5 to the minus 3. So now we have the bases the same for this term, and we just pluck out the exponent. That's the answer for that term. The bases are the same now for this term, so we pluck out the exponent,